Hey everybody, Mr. Covey here. This is 5.7a, proving that figures are special quadrilaterals. And our goal today is to figure out how to prove that a quadrilateral is these different shapes. So last video you saw how to prove a quadrilateral is a parallelogram. Here we're going to look at these special quadrilaterals. Because remember, every quadrilateral is special in its own special way. The first thing we're going to look at is how to prove a rectangle. So the first two ways we're going to talk about proving a rectangle are starting with that quadrilateral already being a parallelogram. So think about your proof. You're going along, either you're given this information or somewhere in your proof you get that DGFE is a parallelogram. If you take this information and you combine it with one right angle, so if you can somehow prove one of your angles is a right angle, putting these two pieces of information together, that you have a parallelogram and that it has one right angle, you can conclude that you have a rectangle. And the statement you'll use is, if it's a parallelogram and one right angle, then it is a rectangle. Okay? So that's one way, is to take a parallelogram plus one right angle, and you can conclude that it's a rectangle. Another way is similar. You still have to have that it's a parallelogram, and you can add on that the diagonals are congruent. So if you use this in a proof, you'd say, if parallelogram, and you show in your proof that the diagonals are congruent, then it's a rectangle. Okay? So these are two new statements we can use in our proof. There's also a way to show that a quadrilateral is a rectangle without first showing that it's a parallelogram, but it's just a little more involved. You have to show that all four angles of a quadrilateral are right. So you have to have quite a lot of evidence there. And then the statement you would use is just, if all four angles of a quad are right, then it's a rectangle. Okay, so if we're going to prove that a quadrilateral is a kite, there's a couple ways we can do this. The first is to rely on our definition, which is two disjoint pairs of consecutive sides are congruent. So if you show that, then you can show that it's a kite. So there's that statement there. Remember that the idea behind showing disjoint sides are congruent is that the sides are next to each other. So for instance, in this one, if you showed AB is congruent to AD, and you combine that with somehow in your proof showing that BC was congruent to CD, then these two statements, if we're doing a flowchart proof, would come together and you could conclude that ADCB is a kite. And your reason would be this new reason we got over here. Because if two disjoint pairs of consecutive sides of a quad are congruent, then it's a kite. Okay, so that's what it would kind of look like in a flowchart proof. There's a way to prove that a quadrilateral is a kite with the diagonals, and that is to show that one diagonal is the perpendicular bisector of the other. And of course, when you write it in a proof, you should write it in if-then form. If one diagonal is a perpendicular bisector of the other in a quadrilateral, then the quadrilateral is a kite. Looking up at our kite here, that would be showing that AC is the perpendicular bisector of BD. So if you were doing your proof and you somehow got that, you could conclude that this shape was a kite based on this reason. On to the rhombus. So kind of like a rectangle, there are ways to prove that a shape is a rhombus starting with a parallelogram. So if you have that a quadrilateral is a parallelogram and you add a pair of consecutive sides are congruent, you can conclude that it's a rhombus. And you only need one pair of consecutive sides are congruent. So if you show that those two sides were congruent, you therefore know it's a rhombus because you know all of the sides must be congruent then. The other way is to show that you have a parallelogram and one of the diagonals bisects two angles. Meaning if you showed that that diagonal bisected angle C and bisected angle A. You can also show a quadrilateral as a rhombus using the side definition. So if you get somehow that all four sides are congruent, you can show that it's a rhombus. And there's also a definition relating to diagonals, and that is that the diagonals are perpendicular bisectors of each other. And again, when we use this in a proof, it should be an if-then form. One thing to notice for this, for a rhombus, you need to show that both diagonals are perpendicular bisectors of each other, not just that one is the perpendicular bisector of the other. The one is just the perpendicular bisector of the other is only sufficient to show that a quadrilateral is a kite. So just be careful about that. Proving a shape is a square is actually not bad at all. You just have to show that it's a rhombus and a rectangle. And that's just based on our definition of what a square is. A square is just a rhombus and a rectangle. It's a romtangle. With proving a quadrilateral is a trapezoid, again, we just use our definition. So you need to show that a pair of opposite sides are parallel. So here, if you showed that AB and DC were parallel, then you could say if a quadrilateral has one pair, or at least one pair of opposite sides parallel, then the quadrilateral is a trapezoid. If you want to get more specific and prove a quadrilateral is a isosceles trapezoid, you need to have proven that it's a trapezoid, and then you need to add on any of these things. So if you had it's a trapezoid and the non-parallel sides are congruent, that is enough to show that it is an isosceles trapezoid. If you show that the parallel sides are congruent, that does not show you that it's an isosceles trapezoid. So be careful about that. You could also show that a quadrilateral is a trapezoid and then add on the fact that the lower and upper base angles are congruent. So for instance, in this trapezoid, you had that it was a trapezoid, and you also showed that angle A was congruent to angle, that angle A was congruent to angle B, and you showed the lower base angles were congruent. That is, you showed C was congruent to D, and you already had that it was a trapezoid. You put these three things together, you could conclude that it was an isosceles trapezoid. Last way is if you have a shape is a trapezoid and you have that the diagonals are congruent, you can conclude it is an isosceles trapezoid. Okay, we're going to look at a little different type of question here. We're going to take these points and we are going to try and see what type of quadrilateral is formed based on how we can show different quadrilaterals. So first thing I'd like you to do is just plot these points on a graph. So do that and then unpause the video, please. Okay, so that's what your quadrilateral should look like roughly. As you might have guessed, we're not just going to say what we think it looks like. We're going to do some calculations based on the coordinates to see what properties we can conclude. First thing we're going to do is calculate the slope of all of the sides. Okay, so let's do the slope of AB. I'll go through this one with you. So it'll be y2 minus y1 over x2 minus x1, which will be 0 over 6, which is 0. So we figure out that the slope of that side is 0. Find the slope of the other three sides. Pause the video and then unpause it, please. Okay, so if you do your slope calculations, those should be your slopes. You should notice something right away, which is that we have two slopes that are the same, meaning side AB and side CD are parallel. Okay, so those give us one parallel side. Those slopes are the same, meaning BD and AC are parallel. So we have right now that it is a parallelogram. We have opposite sides parallel. But it could be something more specific. Maybe it's a rectangle, square, or a rhombus. And looking at our slopes, we actually know it's not a rectangle or a square because these would have to be 90-degree angles, meaning the slopes would have to be opposite reciprocals, and 0 and 2 are not opposite reciprocals. So we can actually get rid of a rectangle and a square. And then what we need to check is, hey, maybe this is a rhombus. Well, based on what you know about a shape being a rhombus, all the sides would have to be congruent. And specifically, we can just check that two consecutive sides are congruent. So let's come down here and let's check if CD is congruent to BD. And we're going to do this, of course, with a distance formula. So to find the distance between C and D, we're going to do the square root, and let's add our x coordinates and square it, and let's add our y coordinates and square it. Calculate that out. You should get, and we're going to do this, of course, with a distance formula. So we're going to find the distance between C and D. So we're going to do the square root. Let's subtract our x coordinates. Square it, add it to what we get when we subtract our y coordinates and square it. Square root of all that, you should get 6 as the distance between C and D. Do the distance between B and D real quick, please. You should get the square root of 20. And what you can conclude then is CD and BD are not congruent, meaning this cannot be a rhombus. Which leads us to say that the most specific name we can say for this quadrilateral is that it is a parallelogram. I want you to go ahead and try this one on your own, and then unpause and check your answers, please. Okay, so to go over what I did real quick, I found all the slopes. I noticed that I had opposite sides parallel, meaning it was at a minimum a parallelogram, but then I noticed that they're in fact opposite reciprocals of each other, meaning they form right angles. So I have a parallelogram that has right angles, meaning I can be more specific than a parallelogram. I can be more specific than a rhombus. It's in fact a rectangle or a square. I went back. I calculated the distance of two consecutive sides. I found out they were the same, meaning the shape has all its sides the same. So no longer am I going to call it a rectangle. I can conclude that it is a square. I'd like you to do this third one on your own and bring it into class tomorrow. And the last thing I'd like to do is this proof. So if you could go ahead and mark the given information and set up a 2-column proof to start, and then unpause. Okay, so to show that ABCD is a trapezoid, we need to show that opposite sides are parallel. So we can mark a few extra things in here. Notice that BAC is an isosceles triangle. So let's call that angle 3. That's the same as angle 1. And since 1's the same as 2, that means 3 and 2 are the same. And then if you look at your picture real quick, 3 and 2 being congruent, since they're alternate interior angles, makes BC parallel to AD. So I'll go ahead and write that up, and then I want you to check. Go ahead and check that your proof looks like this. If you need to pause to look at it, do so. And that concludes 5.7a.